Hello, Midnight Coders, and welcome. Pour yourself a step into this is such a failure. Oh my god, first I'm muted, now I'm tripping. Okay, so pour yourself damn it! I should have practiced this. Oh my god. Oh, step into my igloo and draw and the coffee's on. Pour yourself a cup. I need some apparently.
Yeah, that's so much caffeine in your system, huh?
Right? But oh my god. Okay, so tonight I am joined by Prof, and we are gonna go exploring. Prof, tell us what we're doing tonight.
Yeah,
I'm
yeah.
sipping on
So
my cup. I'm struggling.
I'm gonna tell everyone the backstory of this particular stream. It was trying to figure out what the Java virtual machine does. So for the uninitiated, when you write Java, your code gets compiled to bytecode, and then the bytecode runs on the Java virtual machine. And I was wondering, what the hell does the Java virtual machine actually do? And specifically what I was interested in was virtual threads and how the JVM deals with asynchronous I/O. Turns out the JIT just replaces code all the time, and it's very, very difficult to figure out what the hell Java is actually doing. Extreme pain. So instead of deciphering the entire C source code of the JVM over hundreds of thousands of lines, I decided to just take a look at how different operating systems do asynchronous I/O. And at the end, I'm actually going to show some system call traces of Java programs. Hopefully, Glava here will help me write a few Java programs. And hell yes. And we'll take a look at it. So for those who want to follow along, there is a GitHub link in the description with all the code which is going to get pushed there. Basically, the overview of the stream is as such. We're going to implement a network, like a web server on FreeBSD. Shocker. Bet you never heard of that operating system. We're going to implement the web server on FreeBSD, showing one of the earliest POSIX compliant operating systems with actually good asynchronous I/O, much earlier than Linux. So for reference, KQ, the asynchronous framework we're going to be using today, was added to FreeBSD in the year 2000. So it's not quite the 1900s, but 2000.
Don't call it the 1900s.
And Linux got its own asynchronous I/O framework in 2017, so 17 years later. Though, unfortunately for both of them, as far as I can tell, they were predated by Windows. But you're gonna have to subscribe and come back next time for C on Windows. How does that sound?
That sounds like a tease. I love it.
So, let's get started, I'd say then, huh?
Let's dive in.
Right,
Let's see what you've been cooking.
Let's see what we've been cooking, yeah. So I want to just explain a little bit about FreeBSD. Here I am on a FreeBSD virtual machine. I'm SSH'd in. This is the latest release 15.0.
I've never actually used FreeBSD.
Yeah, dude, they're actually quite famous for their networking implementation. Allegedly, and I haven't had time to benchmark this, their networking system.
What's the difference between FreeBSD and Linux?
Yeah, well, today we're going to see a very large difference in how FreeBSD deals with asynchronous operations versus how Linux deals with it. They're basically incomparable.
Okay. You got me interested. So even
though they look kind of similar, even though you got your awk and grep and clang and all the favorite utilities, at the system call level, they're completely different. And I think that's a nice thing we'll see today, how completely different programming on the two operating systems is. Now, don't be worried. People who think nobody uses FreeBSD, everyone who uses an Apple device has the FreeBSD user space in their device. So what I'm writing here for FreeBSD would work on Mac OS.
So is FreeBSD like a version of Mac OS? Like I thought that was what?
No. So you know what Apple did? They started with the Carnegie University. I don't know their name. I'm sorry, I'm butchering it. But they started with the Mach kernel, and then they put on top of that kernel the FreeBSD user space. So their Darwin OS has two system call APIs. It has the API of Mach and it has the system call API of FreeBSD at the same time.
Interesting. Okay.
So whatever I'm writing today would compile on macOS and run just fine. And in fact, KQ, let me open the man page, man KQ, is the infrastructure I'm going to be using, and its most popular implementation is in macOS. And as I said, famously, FreeBSD is very capable for networking because it's allegedly, I couldn't test this with benchmarks in this week's time, but allegedly their system call implementation of the networking system calls is very efficient, meaning that they're very well suited for high I/O applications. So things like the firmware of switches, of routers, of like things which need to do a lot with the network. Does that kind of make sense?
That's it makes a bit of sense to me. Yeah. Okay.
Right. So here's how I'd approach it. I'd write the server first in a blocking fashion with the completely POSIX compliant system calls which work on both BSD, Linux, macOS, and all of the POSIX-like systems. Then I'm gonna change it over to the FreeBSD specific KQ implementation, and then I'm gonna switch over to Linux and write the client with IO uring. So that's the plan for today. All right, so let me make a directory. Let's go into, let's first make a directory for the synchronous server, just to showcase a little bit of how networking in C++ actually works. Just a second, let me make sure to prepare this properly. All right, here we go. So cd into the synchronous server directory, and that's fine. All right, so I'm going to be using C++, obviously, and I'm going to be using CMake to build it. I'm going to set my CMake minimum required version. I can see that from CMake -- version. That's 3.31, so I'm going to put 3.31 in there. The project is the synchronous server. And what else do I need to put in there? Right, so I'm going to set the CMake standard to 23, the latest one. 26 is not out quite yet.
Well, wouldn't there be a
This
24 before 26?
So C++ gets new standards every 3 years. So
Oh, okay, that's what you mean, 23. Okay, now I see what you mean. Okay.
yeah, 26 is not out yet. Although there's a lot I could say about 26. It's apparently going to be hella exciting. So basically, the settings which I'm setting is saying I want the latest C++ standard. I want this build system to export a compilation commands database so that my NeoVim can hook into that and give me very smart IntelliSense. I am adding maximum warnings, so I want the compiler to warn me about absolutely everything. I'm gonna add a line now which basically tells CMake to just include everything into the project. I'm gonna glob recurse a file for the source, and it's gonna be configured to depend on everything in the source directory which ends in CPP, and everything in the source directory which ends in HPP. And that's about it. I need an executable to build. I want to build the main executable from the source field. And that's pretty much it. So Let's see if I now go and make a source directory, make a build directory, pop into source main.cpp main file here, and we're going to be stuck with only one file. Let's just make sure my build system works by making a quick hello world application. There we go. Now I can go into the build directory, cmake. I'm gonna cmake for the debug build type, meaning we'll get the ability to use a debugger on this. Make it, run it, and it works. There we go. Okay. So the build system is set up correctly. So basically what I did here is more or less generate a pom.xml in Java terms. Like nothing surprising so far. I hope.
No.
Are we all on board so far?
I am myself. If anybody else is lost, though, let me know in the live stream. Let me know in the comments. Let me know in the live chat. There we go. Oh my god, I am struggling this evening, dude. I can't even put a coherent sentence together, and yet you want me to build a little client at the end of this. Oh god.
Yeah, the pressure's on, bro.
Stay tuned
Nah,
if
it's
you want to
okay.
see me struggle on live.
Yeah, struggling life. Alright, don't worry about it. I mean, the beginning is very chill and relaxed, okay? I'm
What are you
gonna
talking about? We're chilling,
chill
man.
too.
I'm chill like a penguin in an igloo eating a popsicle, drinking a coffee.
Nice. That's the perfect way to chill, huh?
Right?
Alright, let me just... Yep, sir. Alright, so I want to make a server, so it means I need to accept connections, right? So let me open up a terminal here. In the end, the system call, we want to call it the accept system call. So this is available on Linux, on BSD, on macOS, on all of the POSIX operating system.
Okay.
And if we look at the man page, it says the argument S is a socket, which has been created with socket and bound to an address. So we
Yeah.
need a socket and we need to bind it to an address. So there are two steps we need to be able to accept connections. Okay. So first of all, let's look at how we get a socket. So let me split the view here and let's go into the source file. So socket. Create an endpoint for communication. I'm gonna need a socket. Oh, but first I'm gonna need an address, even more importantly.
Oh my
Man, I'm gonna need an address because I need to bind the socket to an address. I can't do anything without an address. So I'm gonna use the um, libc utility called getAddrInfo. I think I need man2 getAddrInfo. This is for man3. There we go. Um, this is the C library function which enables us to resolve network addresses.
god. Okay.
Okay, so let's copy over the necessary system libraries. Again, these are system libraries, they are not dependencies. Today we will not be using almost any external dependencies because we're programming from system calls. All right. And I should be clear, every language in the world ever needs to rely on system calls to ultimately get its job done. So that includes Java. Every time you write a Spring application and a Spring server, for example, and that server accepts a connection, in the end, this or that way, it needs to call the same accept system call, which I'm going to be calling now manually. So in a way, what I'm showing you is what Spring does and what Spring abstracts from you on behind the scenes. So pulling back the curtain a little bit on the magic, huh?
Don't scare me, Daddy. I like my hidden
Dude,
magic.
C++26 is getting annotations. Can you believe that?
Oh wow.
We're gonna get Spring++.
I love it. We calling that summer,
Someone, someone needs to make a summer library for C++ networking. That would be amazing.
right?
Hell yeah. All right, so we need to get address info. So we need a host name, a server name, some hints, and a result. So let's take a look at what it says for a host name. This is, by the way, how you program with system calls, right?
It's been so long.
So the host name argument is either pointers to null terminated strings or the null pointer. So I'm allowed to pass the null pointer. That's great. Get adder info. I don't care about the address because I want a local address. All right, let's go back to the top. Then I need a server name, a service name, sorry. Let's take a look at what server name stands for. So the server name is either a decimal port number or null. So I'm gonna specify the port in the service name. Let's make a const char star, so constant character literal, port C string. And I'm gonna use the port 6969, double nice, for
69
my server.
420. Why not 69 420?
All right, if you say so.
Yeah,
69
so,
420, let's do
there we
that.
go. There we go. There we go. There we go.
Pass that port in. So now we need the hints parameter, which passes a pointer to a structure where we can specify what kind of address we want. And here we need to be a little bit specific. So let me make that structure adder info hints. I'm gonna first start by making sure that the memory of this particular struct is 0. So for that, I think I need to include string.h. So I'm gonna memset, std memset, that I think is c string, there we go. Memset that variable to 0, and the amount of bytes I wanna memset is the size of hints. Size of, there we go. And that's gonna be my hints argument. So let's actually set some hints. So the first hint I want is that the AI family, this is address info family. So no chat GPT here.
Jesus, I was gonna say, don't tell me we're doing AI shit.
No AI here. Manual programming from system calls. Hell yeah. So the AI family basically tells me what sort of protocol do I want from the kernel. In this case, I want an internet protocol. So IPv4. Now I want to set the sock type. So that's the socket type, which basically tells me which protocol to use on the socket. That's going to be sock stream, which stands for TCP. And finally, flags is AI passive. So address info passive, meaning I want my own address. Don't go anywhere. Don't use DNS resolution. Just give me my own address. Okay, and the result of this function call is given back to me in the final argument here, the struct adder info pointer pointer. So I need an adder info pointer result. That's gonna be output by the function here. And that this function, if you take a close look, let's just go back to the top. It actually returns an integer. Let's take a look at the return value. I think it's all the way at the bottom. Return. There, return 0 on success or an error code if an error occurs. Okay, so if the return value does not equal 0, sorry, status does not equal 0, we're gonna report a message and quit. So what did I do? No matching function call. And, oh yeah, sorry, I needed to pass the address of the results. There we go. So unlike in Java and C++, we need to be explicit about which variable is an address and which variable, so a reference, and which variable is the actual thing, so to speak. That way, there's no primitive type and class type like incoherence there.
Yeah, C is you gotta be a lot more
There.
explicit. C is a lot lower level than I'm used to.
Yeah, exactly. I mean, these variables here, like for example, this structure is, we can take a look at the definition. Literally, a block of contiguous memory with exactly these variables in them. There's no metadata, no nothing, no garbage collectors. It's just a block of data. So if the status does not succeed, I'm going to print out an error and return. And cannot resolve address, my own address. I'm going to write the error number and the message in there. So the error is going to be the status. And then we can get the message by just passing the status to GAI star error. And I'm going to return exit failure to the system. That's about it. Now, if you take a look at the man page once again, you'll see that there's this free adder info function. Let's look at the man page of that. Right, so after a successful call to get adder info, we need to release the memory using free adder info. So here's some manual memory management for us. Though I'm going to use a C++ trick to make it absolutely guaranteed that this memory will get cleanly cleaned up. And that's by using a stud unique pointer. That's a pointer which has exclusive ownership. This pointer is going to point to an address info struct. And now it's going to have a... Yo, someone's in chat. Ansale is in chat. Hello there.
Hello.
What's up? So this unique pointer is gonna be my cleanup guarantor, so to speak. So if you remember from our last C++ stream, in C++ there's this idea of destructors, right?
Yes.
So at the end of the scope of every object, its destructor gets called. And the unique pointer is... It's next. Yo, what's up, next? Lurking. Thank you. Hope you enjoy it. It is hopefully interesting to you. Though, okay, so since Next is in chat, I know they're interested in Python. I'm gonna finish the stream by showing off how Python does this behind the scenes.
Hell yeah.
Much easier to do than Java because Python is single-threaded.
Oh man, I haven't written actual Python in like I think it was 2013 the last time I used Python.
Oh no.
It's been so long. I used it. Well, okay. Last time I used it was probably 2016. But even then, it was just for a stupid app that I used a Python script to scan a network for movie files, and I wouldn't really call it using Python, but like it was one Python file that did a lot of work.
Yeah, the last time I used Python was I used it to avoid having to use Excel, basically.
I used to use it heavy in the days of IPTV, like before streaming was sort of a mainstreamed thing. Because like the way I used to make money when I came right out of high school was all the local bars used to host the pay-per-view TV things. So I would get bars across the province to basically pay me a fee, and I'll give them this pay-per-view thing for free for it'd be like for like months on end, while instead of them paying yeah, I made a lot of money doing
Oh,
jumping from bar to
I
bar.
also want to make a lot of money.
You just gotta find out what people need, and it's harder now. It used to
Yeah.
be easy, but now all the needs have been met for most people.
Dang, that's a wild story.
Talk to me after the stream. We'll talk about getting you as a instructor for one of my or one of my courses on my project.
Stonks. Hell yeah. Well, I hope people enjoyed this. It may be like a live trial of me instructing people. And speaking of instructing, we're gonna instruct everyone what unique pointer does because it's rather important in the C++ world. Here, I actually downloaded the documentation of the standard C++ library as man pages. So here's the man page of the unique pointer. And what we should pay attention to here is the destructor. The destructor invokes the deleter if the stored pointer is not null. And I can pass the deleter into the template argument here. I'm just passing it a lambda. I'm saying the deleter here just frees the pointer.
Did you know that
And the
Java
pointer is
tech?
here passed.
Did you know that Java
Mhm.
technically has a destructor method or a destructor function in it itself?
Is it try with resource?
No, no, no. There is a legitimate finalize method that gets called
Oh,
on every object that actually destructs all of the objects as themselves. But
oh
you
yeah, yeah, yeah.
you don't explicitly have to call it, so you don't actually ever have to write it in a class. But it is like low level. It's there, and like it technically exists. You can override it if you'd like to.
Damn. Yeah, I looked into finalize back when I was learning Java. There's a big difference to C++. Finalize is called when the garbage collector is about to collect your thing, right?
Yeah, yeah. When it goes to clean it.
Whereas the destructor here gets called exactly on scope exit.
Oh, okay, okay. That's the difference. Okay.
Right? So exactly whenever this function exits, I want to call free adder info on this pointer.
Mhm.
So that's going to be cleanup adder info. That variable is going to be holding that destructor. I mean, the compiler is going to optimize this away anyways, and it's just going to add a free adder info at the end, and it's going to be fine. So that get adder info call gives me my personal address, so that now I can bind that address to a socket. So I need a socket. So socket is a file descriptor, so I'm going to get a sockfd. I love making fun of programmers who are doing networking and telling them they need a lot of socks. Sock short for socket, and
Oh, I know.
but they're
I was gonna
yeah,
make a joke earlier about socks, but I figured I'd
yeah,
not.
programming socks. So
However,
here we're gonna get
however,
ourselves a programming sock. Yeah.
since we're on the topic of TCP clients, I could tell you a UDP joke, but you might not get it.
Oh. Yeah. Okay, I got it.
Did you? It took you a second.
Took me a second. Like, wait, what?
There's a little
Oh, that's
packet
the
loss
point.
there. There's a little packet loss there.
Yeah, the little packet loss indeed. That's
Oh
epic.
man.
All right. Well, that's not good for my networking skills. I'm never getting a job.
Just tell them that joke and see if they get it.
Yeah, if they don't get it, I don't want to work for you.
Exactly, exactly, right?
Yeah, there we go. So let me just say, why did we do this get adder info thing? That because the result now contains our own address, and I can just pass the information on to the socket system call, right? Socket creates an endpoint for communication and returns the corresponding file descriptor. Now, as you can see in the man pages, you can manually fill out the socket properties, but thanks to our get adder info call up here, that's been done for us, and I just need to forward on the particular values I've got. By the way, so this might be a little bit weird to you, this arrow operator. All that is just the dot operator from Java, but when the thing on the left-hand side is a pointer. So it's just a dot
Oh,
operator.
okay. I thought it was lambda. I was gonna say shit.
Now, lambdas have this cursed syntax where you start with a square bracket, then the round bracket, then the curly bracket. The trifecta of brackets for a lambda.
Jesus.
Yeah,
Okay, that's different.
it is different.
That's different
People,
than Java.
yeah, that's very different from Java and most languages. But there's a difference between Java lambdas and C++ lambdas in that the lambda is a new type, basically. It's not an instance of an interface, it's a whole new type. And the
Mm,
lambda can capture things, so I can put captures here if I want. But you
okay.
have to explicitly ask for captures. The Lambda doesn't capture stuff automatically.
Now, by capture, is that a return type? Like, is it like that, or is it like a
No, that means I can
parenthesis?
use local variables.
Oh, okay, okay.
Okay. So socket returns -1 if an error occurs, or we get a file descriptor which works. So if the sockfd is less than 0, I'm gonna std println for debugging purposes. Couldn't
Table
get
flag.
a sock, so I'm gonna put the error no here, and I'm gonna use stir error on error no here. There we go. So stir error is just a function which explains the error number. In any case, we are gonna return exit failure here too. And because this is a destructor, by the way, implicitly before the return, the destructor will get called and no memory leaks.
Woohoo.
And we're gonna need another one of these destructors right now. Actually, not yet. I'm not gonna close the socket yet. I'm only gonna, because this is a server, I need a socket to stay alive. So no closing the socket. All right, so now that I have a socket, I want to change one of its properties. So one option, which is just a convenience, but it will be helpful. So I'm going to set sock opt it, and particularly the socket option I'm interested in is reuse adder. Enables local address reuse. It basically means if I stop the server and then restart it very quickly, the kernel will allow me to reuse the same address without throwing an error address in use.
Ah, okay.
It's a convenience, but let's just do it. So we want set sock opt. And let's really quick look at the man pages here. So that's from systypes.h. I think the LSP included everything nice. So the socket is sockfd. The integer is not accept. What is it? Man set sock opt. Integer level, right? So the level is the level of a socket. Now I want the operation. I want to reuse the address. Now I need to set the value of the option, and the value of the option is true. Now, unfortunately, since this is a C API, true is represented as 1. So let's just make this context. Let me just make this a constant int 1.
Is there no Boolean value in C, like true or false?
And in C, no, unfortunately not. You're required to use integers.
Oh wow, that seems like a memory waste.
Yeah, it is a way. And the compilers are very good at optimizing those integers away. But for now, we need to use an integer true here and pass its address over. So that's what I did. And if we look at the return value, upon successful completion, 0 is returned. So let's say if int status equal to that, status less than 0 would be the error condition. Std print ln couldn't set socket option. This is not a fatal error for my program, so I'm not going to exit. I'm just going to ignore this error and log it. Okay, so now we are ready to do the big balls bind.
Big balls bind.
So
Oh my god.
Yeah, this is the risky system call, right? Because this reserves a local address. Man2 bind is a system call. So whenever I do man2, the second category of man, as you can see here, is the FreeBSD system calls manual. So that's why I did man2, because I want specifically the FreeBSD system call, man2 bind. This is the risky system call again because it asks the kernel to reserve an address for us. And that may fail. And obviously that returns an error code, status. It's bind. So we want to bind our socket to an address. And thanks to our previous use of get adder info, I can just pass on the data given to us before. So unfortunately here, due to C heritage, we need to pass the kernel the length, or rather the size of this particular struct. But again, get other info does that for us and puts it in this field here. So
Okay.
if status is less than 0, then we're going to print ln that bind failed. And this is a fatal error. We cannot deal with it, because that means we cannot get a local address.
Okay.
There we go, and I'm gonna return
Return.
exit failure. Alright, so now that we have bound the socket, we can listen on it. So now that we get an address, we can listen on that address. So listen counterintuitively only tells the kernel, please get ready to accept. So to accept, we need to put the socket in the listening state. So we can do that very easily. Again, this is an infallible function, so we need to check the return value. Listen to my sock, and with a backlog of just one. For now, we're going to be accepting one connection at a time, and that's fine. I think on most operating systems, the kernel allows you to have a backlog of about 15 to 20 connections. But for now, for our demo purposes, one backlog is more than enough. Again, if we can't listen, so if I say status less than 0, that's a fatal error. It means we will not be able to accept anything. Let's just
That's
say
correct.
failed. That's another exit with a failure. And finally, we are ready to accept connection. So I'm going to use a loop. This is yet another one of my patented programs which need to be exited using Task Manager because they don't have a graceful exit. It is what it is. Don't worry about it.
It is what it is. Who cares? YOLO.
Yeah, well, yeah. So we're going to accept here. So let's look at man accept. We need the first argument is the sock. So this is Python. Someone asks in chat. No, this is not Python. This is what Python does behind the scenes. And actually, since you're asking about Python,
This is C++.
Python connect. There we go. So in the library socket.py, you have C bindings to the functions, which I'm calling right now. So yes, technically this could also be Python. But no, I'm using system calls, not an interpreted language. Relax.
Relax.
All right,
Oh
so.
my god. Chillax, bro. Just chillax. You got this.
All right, so
My beer.
let's look at the description. The argument S is a socket which has been created with socket bound to an address with bind and is listening. And this is what we did, right? So we created it with a socket, bound it, listening on it. You're brand new to programming. You're trying to learn HTML and CSS right now. Sorry, I didn't mean to interrupt. No, it's fine. And especially since you're learning HTML, this is what the current has to do behind the scenes every time you want to serve your HTML page over to some client. So when you type in google.com, what that does is it sends a request to Google server, and then Google server, via the same mechanism which I'm using right now, responds with an HTML file. And specifically, now this is a Linux specific thing, so I'm gonna have to use the Linux man pages. Linux has a send file system call, which is specifically optimized for sending files across the network. So this system call is what every single, well, I hope every single web server uses to serve HTML. They can never trust Java, am I right? Anyway.
Really though. Really though. As we'll find out later on when they say, yeah.
Yeah, as we'll find out later on. Yeah. All right, listen. Sorry, I did listen. I need man accept. I want to accept stuff. I need some acceptance in my life. So let me see. The argument S is a socket, right? So we need to accept on the socket FD. And the other two parameters are actually out parameters. So we need a sock adder pointer. So sock adder out address. So let's pass the pointer to that. And the socklen. So let's pass that sucklin,
These
pass
are
it as an
knee,
address,
these are these are
and
knee
then
these are knee-high socks,
mhm,
not ankle socks.
yeah, yeah. Where are the Rust programmers now when we need them, huh? So accept either returns -1 on error, or if it succeeds, returns a file descriptor. So this is the client's file descriptor, which is accept. So first of all, if the client FD is less than 0, then like there's an accept error. So println accept error. Trying again. Let's just pass over the
Good luck
error
next time,
number
bro.
for debugging purpose. Huh?
Good luck next time, bro.
Yeah, well, it may happen that the client suddenly disconnects, for example.
Yeah. Bad internet,
And
bad service, something like that. Yeah.
yeah,
Hmm.
so that, and I'm just gonna say continue. Please. Not a fatal error, one accept failure is fine. So otherwise, I need to clean up the socket. So I'm gonna use the same cleanup trick. This time it's gonna be pointing to an integer. And the cleanup will be, again, another cursed lambda. It's gonna take an integer pointer, and what it's gonna do to it is gonna close it. I need a semicolon in the lambda close. Oh, for close, I need to include uni_std.h. Close the file descriptor. That's a csock, the client's sock cleanup of the address of the client file descriptor. There we go. That's just for cleanup purposes. Now we have the client's socket. Now we can write to the client. So let's do man write. That's the wrong man. Man2 write. Again, 2 is the category of system call. It's from uni_std, which I just included, and it again returns a size. So it returns a signed size t, which is a long, written, so how many bytes were written. So write into the client's file descriptor a message. So let's make our message. Let's say, hi mom, or something like that. And let's pass on the message. And we need the number of bytes. We're just going to do strlen of message. And actually, I'm going to do +1. Now, the reason for the +1, so if you look at man strlen, you'll see that, and if we go, wait, sorry, terminator. Right, so the number of characters that precede the null character. I actually want to send the null character too, so that the guy reading can determine when the message is over.
Okay.
So let's write that to the client. Let's say, so if written is less than 0, then an error occurred. So, and there's a lot of errors which can occur. For example, the client is connecting, again, is an error on the right. It's not a fatal error. I mean, there will be other clients. And just continue. That's going to continue in either case. So there we go. So that's a blocking web server. Let's actually see if this builds, if I didn't make any mistakes. It does build, and let's run it. Service was not recognized for socket type. So that cannot resolve my own. Maybe 69,420 is too big, huh?
Maybe. Just try 6969.
Yeah,
69
the
ports.
AI points out that the largest port number is
Ah, yes,
65,000.
65,000. Yeah, that's the size of a boat.
Bruh,
Or
Spring
yeah.
developer much?
You know what? Go with 42069. Go with 42069. Just move this
Yeah, that
69.
doesn't work. Yeah, just make a switcheroo. There we go. The server is now listening for connections. I'm gonna connect to it from my Linux machine. So let's go telnet there on the port
420.
42069. And there we go. There's the message. I forgot the new line. Oh my god, I forgot the new line.
Oh, you failed.
Big fail.
Way to go, man.
Let's
Now
remake
we
it
now now we
main.
got now we gotta do it again.
There you go. Telnet. There you go. Hi mom. There you go.
Hey,
That's a web server for you.
hi mom.
So to the guy in chat, all you have to do is now instead of writing hi mom, you need to spit out HTML at your client, and you have a web server. That's it.
At least
All
for a
right.
homepage.
So this is a synchronous web server written in FreeBSD using system calls. So what makes this synchronous? So now let's explain a few things. First of all, so there's nothing horribly bad about any of these system calls here. The main problem we have here is this accept. This accept call waits for an incoming connection. So it blocks. Now what does blocking mean? It means, well, I call the system call, the system realizes, there are multiple languages you're gonna have to learn. Yuktra said in chat, oh hell yeah.
Mm-hmm.
At the very least, you're gonna need HTML, CSS, and JavaScript if you want to use Node.js on the back end.
Yeah,
But
if you're looking
probably
at
you're gonna
if
need,
you're looking to be a web dev, there's three languages right off the get go that you have to know, which are
yeah.
like he said, JavaScript, CSS, and HTML.
Yeah, there's just no way around those three. But if you want to be a real Chad programmer, then you're supposed to do the backend in Java.
Well,
And
some
that's what this channel is
some
all about.
some people use Python. Us pros decide to use Java because we're all caffeinated nerds.
Yeah. Yeah, people are allowed to have incorrect opinions, am I right?
Well, I mean, well, I can't get into that. Never mind. Never mind. Let's just go. I won't get into that.
Okay, so what I was saying, when I call accept, I'm telling the system, please give me the next connection. And the system is like, well, there's no connections. It just got started a week ago. Damn,
Just
Yutra is, yeah, well, good luck,
damn,
bro.
and you're not writing your own web
Thanks.
servers yet or your own compiler, man. What's wrong with you? You're a week in.
Yeah,
You
what's
got
wrong with
this.
you? Why you
You
not
should be a
using
senior by
syscalls,
now.
bro?
You should be a senior dev by now.
Yeah.
Don't you know what full stack means?
Yeah. So, anyways, let me explain accept. So, when the system, FreeBSD in this case, realizes there are no connections, it's gonna unschedule my process. It's gonna say, well, you're waiting. Let's give the CPU to someone else. And this is the essence of blocking. It's getting into a situation where, because of doing nothing, you are unscheduled and your process makes no progress. Okay? So that's the number one thing we want to avoid. We don't want our threads to get unscheduled because then all of the stack space of the thread, and mind you, for example, on Linux, the stack space by default is 8 megabytes. So it's 8 megabytes of RAM is just sitting there unused.
Mm-hmm.
So the idea is we want to let the system wait in the background because waiting on scheduling takes no CPU anyways. We want to do something else during that time. And again, an easy solution to this would be to just use more threads for head, but just using more threads requires a lot more memory. And also, creating threads is rather expensive. So that's why we need an asynchronous API for networking, and that's why I'm gonna show you how to use KQ on FreeBSD to write this same server, but completely asynchronously, meaning it's now going to be capable of
Not
handling multiple concurrent connections with just a single thread. So let me just yoink the CMake list from this one and paste it here. I'll need to make a few changes. Oops. So now this is the asynchronous server. All right, so everything else is the same build system. Let's add a main.cpp file. Let's just real quick make a main function. Let's include print stud print ln. Hello.
like
I don't need a new line.
Like from over
Add this.
here.
There we go. Write it. Write it. Terminal. Go into the build directory. CMake. I'm gonna again CMake build type is equal to debug. Make it. There you go, main, and it works. All right, there you go. So that's that. Let's get Clang D to help me out here. Format it. There we go. All right. So what are we going to be doing? We are going to be using KQ. There's a pair of two system calls on BSD and macOS. Again, both of these implement this. Also OpenBSD, any of the BSD versions. So the KQ system calls provides a generic method of notifying the user when an event happens or a condition holds. This is exactly what we want, right? We want to get notified when there is an incoming connection. Does that make sense?
Mm-hmm.
So I would like the system to be like, hey, yo, there is a connection incoming, wake up.
Mm-hmm. Wake up and do
And
something.
the KQ system call is going to enable me to do that, or any other of a myriad of possible conditions. So with a KQ, we obtain a Q file descriptor, and then with the man K event, with the K event system call, we can inform the kernel which events we are interested in. So this is basically an edge-triggered mechanism. What does it mean, edge-triggered? It gets triggered whenever a condition begins to hold. Okay? So we need to be careful about resetting the event. Also, we need to still do the dirty work ourselves. Right? The kernel doesn't do anything more. It just tells us, hey, oh, it's time for you. And then we know that our next call is not going to block. And that's the information we're getting. All right. Now let me just for a second make sure I have my prep ready because this is actually quite difficult to write. I cannot lie. It's still going to be a single C++ file. Don't you worry about that. So let's go back to main.c. All right. So I'm going to need a few things, unfortunately. Actually, let's just get started. Okay, so we're going to have a KQ object, which is a file descriptor. We're just going to call it KQ. And the first thing we're going to do is we're going to try and get one. So unknown identifier, that does make sense. Let's just check out the man2 KQ. That one comes from sysevent.h. So let's include /event.h. This is now far away from Linux territory. Linus Torvalds is now watching and crying. This is not possible on his operating system. I'm partially kidding. If you look at the GitHub link I posted, yeah, partially. So with system calls, this is impossible. But there is a user space compatibility layer developed on Linux, which is called libkq, where basically the library pretends like there's a KQ for you on Linux. So you could technically write this on Linux too with the library role-playing the mediator there. The link to that is on the README of the GitHub repo in the description if anyone wants to check that out. In any case, I want the KQ. And if I don't get it, I'm going to whine about it. So if it's less than 0, let's check the return value.
Sounds like a few people I know.
Yep, I'm going to whine about it and I'm going to be a failure. Cannot get the KQ.
God, that sounds more like.
So let's pass over the error notes to error and return exit failure. So we need a KQ. All right. Not really much we can do about that if that fails. This is a very, very, very rarely failing system call, so don't worry about it. And it is what it is. So since we're going to be doing this asynchronously, I'm actually going to implement an exception type, by the way. I'm going to just implement a syscall exception. It's going to be a super simple exception. It's just going to inherit from the runtime error. So yeah, this is C++ inheritance. You use the column for that. And I'm gonna give it a constructor which takes as an argument the error number, and just time error syscall error. By the way, I'm gonna give it an optional syscall argument so that I can add a system call explanation if I want to.
Okay.
So here the first argument is gonna be, oh, by the way, I want to format format.
There's
There we
so
go.
many STDs in C++.
Uh-huh. Not
They're
suspect at
everywhere.
all.
They're everywhere.
I'm gonna show you something a little bit cursed about C++ in a second, and every C++ programmer in the chat is gonna roll their eyes at me, but it's true. So let's say, so the first thing is the syscall, which then the number, then the message. Syscall, error number, and stir error of the error number. And that's it. It's a simple exception type, and I'm gonna wrap the rest of the main function in a try catch to try and catch that. So syscall exception, and I'm just gonna print the println the exception dot what. The what method gives me the message. No, I accidentally closed it. That's a mistake. There we go. And I'm gonna return a good failure. Got an exception in my brain cells. Anyways, this is what we're gonna use to like simplify the error handling just a little bit. But anyway, so the starting part of this asynchronous server is completely identical to the synchronous one. So we still need an address for ourselves. We still need a socket. And we still need to set it to reduce address. The socket system call is not blocking because we are requesting local system resources. Also bind is not blocking because once again we are requesting local system resources. Let me copy over the includes here just to make sure we are on the same page as the previous implementation. There we go. I need my port number once again. It's going to be a constant global variable. And that's pretty much it. So same thing as before, we're going to get the address info, we're going to get ourselves a socket, and we're going to bind to it. That's all the same. No differences there. Now is the tricky time where we want to accept something. So I need to accept stuff, meaning I need to wait to be able to accept something in the first place. Let me zoom out a little bit because now we're going to need to be reading man pages like a very reader, let's say. K event is the system call in question. So take a look at this. So it's a one system call, K event, which does everything for us. So it takes the KQ as the first argument. Then it takes a list of changed events. So an array of changed events. So these are the changes we're making. We're telling the kernel, okay, now we are interested in this new list of events. Here's the number of changes, so the size of this array. And then the kernel is at the same time giving us back the events which are currently active. So the conditions which are currently fulfilled. So the K event both submits changes and retrieves the current status of the system for waiting or whatever we want to do. Okay?
Damn.
And out the K event structure, so struct K event, and this is going to be the accept ready event. Right? So we want to be ready. Oh, by the way, I completely missed something. I had a little stupid moment by copy pasting here. Yeah, actually not yet. That's fine. This is all fine. We need to know when we are ready. Sorry, and that's what we are gonna set up this structure for. So let's just take a look. There should be a K event structure. So struct K event. There we go. Those are the fields of the struct. We need to fill them out. So the identifier for the event. And the event we want is the accept event. Accept. Where is it? ManKQ, maybe here. Accept. Oh, sorry. There's no accept event. There is only a read event, but reading from a bound socket is equivalent to accepting in the eyes of FreeBSD. So what we actually want is the read filter. Read. There we go. Takes a descriptor as an identifier and returns whenever there is data available to be read. So I'm asking the kernel, please tell me when there is something available to be read. And here it says sockets which have previously been passed to listen return when there is an incoming connection pending. This is what we want. All right. This is exactly what I want. So let's see what it says. So it says takes a descriptor as the identifier. So the identifier is the socket's file descriptor. And there's a little bit of casting necessary here because the structure has enough space for any 64-bit type. The socket file descriptor is an integer, which is 32 bits, but I'm just going to cast it. So next we want the filter, which is the filter read, as I said. We need flags. The flags configure this. So obviously I want to add this to the events I'm interested in. And also I want to, sorry, what am I doing? Quit. There you go. I also want to clear. Yeah, wrong hotkey. Yeah, I'm sorry. So where do we go? Yeah. So the other flag is EV clear, which says resets the state of the event immediately after it's retrieved. So I don't want to be notified twice. I want to get the event reset immediately after it clears. So on EV filter read, FF flags don't matter. So FF flags I can just set to 0. Let's go back to the man K event and let's destruct K event. The structure, right? So now it has the filter data value. I need to, that depends obviously on what filter we want. In the case of read, there is no additional data we need. So I'm just gonna, yeah, there we go. Data is just 0. The next thing we need is the user data. And here we have a slight problem. So here we're gonna do something very cool in a sec. I'm just gonna put it to null pointer just for a second here, but we're gonna change it. Let me make a to-do. And there's some extended data, which in this case is an array full of zeros. We don't need it. Okay, so if we read about udata is an opaque user-defined value passed through the kernel unchanged. This is really useful. So this might look like pointless to you because the kernel specifically says I'm not going to do anything to this, right? But actually what this allows us is to have a hook basically which refers to whatever we want to do after the event succeeds. Now that kind of makes sense?
Yeah.
I'm submitting an event and then sometime later I'm going to get it back, but I don't know in which order or which events I'm going to get. So the only way I can know that is by passing some note in udata. And udata is just 64 bits. It's a very small object. So the only thing we can pack into here is a pointer, a single address. That's all the kernel allows us to have as the reference to wherever we left off. So what I'm gonna do here is I'm actually gonna put a reference to the handler here, to handler. And here we're gonna use a nice little programming technique from Java, known as object-oriented programming and specifically polymorphism. Yes, polymorphism in C++, you're gonna make this absolutely beautiful. So here's what we're gonna do. We're gonna define an interface. Now in C++, interfaces are just normal structs. So I'm gonna have a handler interface. And it's going to have a virtual method. So a virtual method is one which is able to be overridden. And all it's going to do is going to say handle yourself. And it's going to take a struct k event pointer, which is my event. So I'm going to pass it the event which just caused me to call it. And I'm going to set this function equal to 0. So equal 0 in C++ means it's abstract. So in this case, it's an interface, which because it has a single abstract method. And now I can implement that in my handler. So for example, let's make an accept handler, which inherits from handler. Let's override that function. So C++ actually has an event pointer, my event. Actually has an override the keyword, which checks that we properly override it. There we go. And now we want to handle the accept condition being true. So first of all, we're going to need to do some manual memory management. We need a structure object of accept handler, which is a pointer. We need it to outlive the current function, right? Because we're going to continue with the request later in a different function, which is why I need to heap allocate it with new. Now, mind you, in C++, there is no garbage collector, so I need to manually also unallocate it later, which I will do in the completion handler. There's a new accept handler. There you go. No constructor params necessary. And I'm going to pass accept handler here as the user data. So now, whenever this event is executed, it's going to return with a reference to the accept handler itself, which means I can just use this pointer polymorphically and call handle yourself on the pointer in the handler. It's going to make it very easy. So let's actually submit this event to the kernel. For that, I need to look at k event once again. So this is a fallible function. Return. Right, so it returns -1 if something goes bad. So let's get the status. K event system call. So here I need the K queue. This is the queue. My change list is just going to consist of one item, which is the accept ready event, with one single change. I don't care about incoming events right now. I don't want any of them, and I don't want a timeout. So let's see that. Status less than 0. Once again, it's absolutely necessary that we are able to submit this to K event. So this is a fatal error. Let's just add a message. Actually, here I can just throw syscall exception with the error number inside of it, and that's it. And actually, I'm going to say K event as the system call, which failed. Nice. So that's really easy error handling here with the exception, which I just defined. Perfect. And so for now, this is done. So here I'm just going to run a function, which I'm going to call worker routine. This is basically going to be our loop. Let me define it up top. The worker routine is going to be the event loop, which waits for the asynchronous operations. So let's say here to do. Okay, so accept, handle yourself. How am I supposed to handle? Oh, by the way, the worker routine is going to be very simple. So the worker routine, let's actually implement it first. That's because it's just shockingly simple. While true, it's going to be a while true loop. I want to see which event, what's up with the kernel. So new event, and I'm going to do k event. So this time I'm again using the k queue. I don't have any changes this time. So this time I'm going to pass null pointer here and no changes. Now I want a single change in the new events, and I want to wait for it indefinitely. Null pointer type, just null pointer. And again, we need to check that this actually succeeds. Because again, if this doesn't, so in this case, it does, they can just continue looping, that's fine. I'm gonna log it. fail, let's say skipping. By the way, what's really important here to set this to 0. The bad way to do it is mem set my event to 0 and size of my event. There we go. Skipping, and then the event is the error is error no and error no. Oh, sorry, not my event, it's new event. I made a typo. There we go. So this basically waits for a new event to be available in the KQ and gets it in this new event variable.
Okay.
Now, remember what I did? I put in the new event dot. By the way, yeah, we want to check them. So if the new event dot user data is a null pointer, it means that nothing was retrieved, right? So we set the struct to 0 and null pointer is 0. So if it's 0, we're just going to continue. I'm going to log that too because it's a little bit suspect.
Logs are good. Logs are good.
Got event, but nothing changed. Let's say skipping. All right, so if it's null pointer, then forget about it. Now, if it is not a null pointer, then we know it's a pointer to a handler. So I'm going to static cast it because, again, through the kernel, everything passes as a void pointer. And void doesn't have type data, but I want to cast it to a handler pointer of new event dot udata. And handler, handle yourself with the new event.
I love that.
There you go.
That's a great name. Good naming on that. Good naming.
Yeah, naming conventions. Absolutely professional. Microshit, hire me.
Micro shit. Oh fuck.
Oh wait, I wasn't supposed to call them that. They were supposed to call them microslop. My bad.
Well, someone's got sloppy shits.
Yeah. Yeah, Windows is completely different. I need someone in chat to tell me whether next week I should do the same thing but on Windows. It's completely different and really highlights the difference of the operating system. But anyway, look at how simple it is to make an event loop. This is JavaScript in a nutshell. This is the JavaScript event loop, just a while true loop waiting for events and telling them to handle themselves. It's so easy. All right, now we actually need to write the handlers because like we ain't there yet. Let me just make sure I am looking at my correct notes just in case. There we go. Oh, okay. So we need to add something to the accept handler. We need a socket. So my
More
accept handler
socks.
needs a sock.
More socks.
And here I need to pass it to the accept handler. Actually, and because I didn't make a constructor, I need to actually make it. Oh, by the way, okay, I need to do two things. So let's say this is the incoming sock. I'm gonna initialize my sock by the incoming sock, and that's it. I forgot a very important thing here, which is to declare the destructor virtual. And I'm gonna just default it. That way, stuff gets deleted properly. Right, because if the destructor is not overridden, then whenever a derived class gets deleted through a reference to the base class, only the base class destructor gets called, and we completely forget about the rest of the derived class. It's a disaster waiting to happen. Always remember to mark the destructor as virtual.
Interesting.
I am frankly shocked that this is not the default, but every compiler will cry about it if you forget it, so let's say it's good enough.
C seems like such a touchy language.
Yeah, it is such a touchy language indeed. All right, so we want to call accept, right? So the accept event has happened, and we can now accept. And specifically, I can even call the special accept for system call, which accepts flags. So if I take a look at what the flags can be, let's see. I can actually I can actually say accept this without blocking, which again is guaranteed to work because I just waited for the event to be ready.
Hmm.
So since this accept handler is allocated with new, we need to delete it by the end of this function. So I'm gonna basically put the delete myself at the end of this into another unique pointer, which is accept handler, and then it's just gonna
STDKMS.
delete myself of this. Again, this is because clean up myself from memory. Not the cleanest way to do it. Ideally, you'd have a smarter memory management solution. Fine, it's fine for now.
Mm.
Anyway, so we want to accept. To accept, we need a client address, right? We're going to get a client file descriptor. So int client, the client sock. We're enjoying socks all over the place here, huh? So the integer is my own sock where I'm accepting from. And then we're gonna get as output the client's address and the client sock length. Okay, so sock adder client adder and sock len
I will be.
client length.
You can keep going. I'll be back in just one quick second. I gotta run to
No problem.
too much coffee and not enough blabber.
So we need sock non-block. So let's take a look here at man accept for sock non-block. There you go. So we can say I want a non-blocking connection to the client because we're going to use KQ to inform us when we can write or read without blocking. If I take a look, this is included in systypes.h. Yeah, we do have that. Okay, perfect. The reason for the error here is that these are supposed to be passed as pointers. There we go. So if the client sock is less than 0, then we have an error accepting. So here we should be careful. So yeah, I mean, if we have an error accepting, we don't need to be careful. We're just gonna wait for the next one. So I'm just gonna log println failed to accept connection. Another log. I'm gonna pass the error number and the message, and be done with it. I'm gonna return. I'm just gonna return out of the handler here. That will, by the way, of course, clean myself up. Anyway, so if the client socket actually is a valid socket, we need to call write. But once again, write is a blocking call. So I'm gonna, instead of that, wait for a blocking call to be non-blocking,
Wow.
right? So
Apparently
I'm
my
gonna use
headset.
the KQ.
Apparently my headset turned off. I'm back.
You're back. And I'm just about to submit the second request to KQ, a write request.
All right.
Yeah, time to write.
All right. Let's ride.
So let me just make sure I'm doing this properly. Yeah, that's all good. So once again, we are gonna make a struct k event to inform the kernel of what I want to do. I want to write. So let's start with the ident. So actually, we need to know what the filter is first. Let me take a look at the man page for KQ once again. I want the damn it. I want the filter for write. It takes the file descriptors identifier. So the identifier here, I want to write to the client socket. So the client socket identifier. And once again, for type safety reasons, I have to cast it to a 64-bit type. The filter, so the event I'm interested in is in the if filter write. I want to be able to write. The flags here, once again, are ev add. I want to add this filter, and I want to do it only once. So ev dispatch. So if you take a look at once again here at the ev dispatch, the man page for that. disable the event source immediately after delivery of an event. So as soon as the write event gets delivered, it's going to get disabled because I only want to write once. That's why I'm going to put dispatch FF flags in the write case, as you can see here. Let's go back to write. FF flags doesn't take anything, so we're just going to put it to 0. The data, again, doesn't take anything. Now the user data, again, is going to have my handler in it. So now we need to implement a different handler. Let me just put null pointer here. And to do implement write handler. See, and that's where polymorphism is going to come in so nicely. I'm just going to derive another class from the handler type, and it's going to be Bing chilling. Strange coding brace here. Okay. Back to simply. Yeah, there we go. All right, perfect. We don't need this now. All right. So that's the write event. I'm going to add the handler in a sec. Let me just submit it to the K queue real quick. Once again, that may fail. So I'm going to K event, the K queue. It's going to be the write event, which I want to submit. It's a single event. And I don't want to retrieve any events right now. So 0 retrieved events, and the timeout doesn't matter. Status less than 0. So if I cannot enqueue this, well, there's not really much I can do in that case. I'm going to log it. It cannot register write request. And then I'm going to pass in the error number and the explanation. I'm going to close the connection to the client. That's rather important. Otherwise, the client is left hanging, and we never want to ghost people.
Right? Never leave a man hanging.
Yeah. Did I do something incorrectly? Oh, I am. Error. And I'm going to return it.
You gotta spell it right. You just gotta spell it right.
Yeah, you just gotta spell it right. Okay, let's implement the write handler. And since C++ is read top to bottom, I need to implement it above here. So struct write handler. It's gonna derive from the handler, and we need to get the handle yourself function with a K event my event once again. Override that, and there we go. Let me put a semicolon there. Okay, so now we need to handle the write request, and that one is going to be a little bit difficult. Let me explain real quick why.
Now we get
The fact of the matter,
stuff.
it's not really that difficult. It's a little bit tricky. And if you take a look at man write, it returns how many bytes were written, which may not be everything. You may make a write request, and the kernel will be like, I could only write part of it. Sorry. So in that case, we will need to repeat our request and do it again. So here we need to be like really careful. Because there's a little memory management issue. Okay. So we need to know for this what we are writing. So we have a constructor, which is the actual message. And we need to know the file descriptor we are writing to. Let me implement a quick constructor. Now, you may be asking why does this constructor not get implemented automatically? This is because we are using polymorphic inheritance, and that tells the compiler that we may be up to weird in the constructor, and so it doesn't implement it automatically. Also because the constructor may be polymorphic, unfortunately. But none of that weirdness for now. Let's just take an incoming message and a file descriptor. And let's initialize our message from the incoming message and our file descriptor from the incoming file descriptor, and that's it. So now we know what to write to. Let's see. So if we take a look at man k event, kq, sorry, and we take a look at if felt write once again, you'll see that data here will contain the number of space remaining in the write buffer. So this is how many bytes we can write. So let's say the number of buffers, space to write, let's say, is the event data. Okay, that's what we read from the message. So how much do we want to write? Let's say want to write is, well, the strlen of the message plus the null terminator. So first of all, if I want to write just the null terminator, then there's not really much to do. We're done. And delete this because we are done with this object. Now, if we want to do more, we need to deal with the possibility that not everything is written. And for that, I'm going to use another lambda. So let's make a lambda variable here, enqueue continuation write. Right? So it's basically going to be a function which just enqueues, as I said, the continuation write. I'm going to capture everything by reference, so all of the scope from the reference, and I'm going to take as the only argument the number of bytes written. I'm going to take the message and increment it by the number of bytes written. Now we're going to need another event, which we are submitting to the FreeBSD kernel. So the continue writing event, I'm going to call it the continue writing event. Let's fill up this event once again. So the identifier is the exact same thing. Actually, what we can do right here is be a little bit sneaky. We can copy the event which we got already, and we can just change a few things. So most of the flags are the same. It's just that the continue writing events data is now this. And I'm not going to delete this, right? So this object now survives because it's going to be used whenever this event gets triggered. Everything else stays the same. I can just copy it over. Right? And let's just say, once again, I'm going to submit it to the K event queue. K event, the K queue. The changes is a single continue writing event. Null pointer, no events together, 0, null pointer. And once again, if the status is less than 0, std println cannot enqueue continuation rate. And it's going to return. By the way, this is a lambda. I need to put a semicolon at the end of it. There we go. So otherwise, if this is successful, oh, by the way, before returning here, we need to delete ourselves. Almost forgot, there was a memory leak. That's how we enqueue the continuation rate. We just increment the message pointer. So we go forwards by how much we've written, and we say write again from that point. So that lambda is going to come in very helpful. So if the space we have to write, oops, that's a wild autocomplete. If the space we have to write is less than how much we want to write, then we need to be careful. Let's say long written is equal to, again, write. The file descriptor is the file descriptor which got passed to this handler. The message is the same message, and I want to write as much as there is space to write. All right. So once again, the write call may fail. Again, that could happen, for example, if the client disconnects or something. If it's less than 0, std println a write failure. And let's just put the error in there instead. And technically speaking, and of course someone in the chat may want to do this, there's a many cleaner memory management and error logging, error handling approaches than this. I'm just doing this for a proof of concept code, and I do want to acknowledge the possibility of errors. I don't want to just ignore them. But implementing a proper exception handling framework, something like Spring's exception handling framework, would be very difficult here. And also very laborious, and I really don't have 10 hours to stream today. All right. So if the writing fails, then it fails. Otherwise, I'm going to include a continuation right, and this is how much is written. So here the lambda is coming in very nicely. It's very useful. So else, if there is enough space to write, I'm going to copy this line, but then I want to write the message length. So how much I want to write. This is more or less the same. I'm going to copy paste the error case. And if we are done, so in this case, we're all done. I'm just going to close the file descriptor because no more writing to it. And I'm going to delete this. All right, so that's the write handler. Now we can actually use the write handler in the accept handler. So let's say, oops, what did I do? There we go. Write handler pointer, write handler. I'm going to heap allocate it once again. And the write handler wants a message. And the message is going to be hello, mom from FreeBSD. And the file descriptor is going to be the client socket. Client socket. Haha.
More socks.
There we go. Socks. Knock your socks off. Haha. User data is write event, and I need to cast that to a void pointer. Oh, sorry, not write event, write handler. Never name your variables too similarly. Okay, so
I love
we've got the.
love ambiguous.
You do?
Fuck no. You're fantastic, man.
All right, let's once again. All right, there we go. Let's try it. So here we have started it. I am now gonna. Oh, this is not good. Let me. This is not good. That's not great. Come on, main. There we go. And let's telnet connection refused. What did I do wrong here?
It's up and running, right?
Yeah, it is up and running. Okay, well now it's time to debug this. Let me just make sure I actually programmed everything I wanted to program. Um, Steps event. Okay, worker routine. Let's just say here waiting for event. Let me make sure we're getting to this point. Time for a little bit of debugging. I'm not sure what I messed up here. Am I in the wrong directory, by the way? No, I'm not. So I did actually waiting for events.
Okay. So
Let me make sure I have the correct events here. Have EV clear, yes.
your laptop battery is at perfect percent. Oh.
So I'm actually wondering why this is not doing. Let me try with another second term. Let me just telnet local host for 2069. Connection refused. Okay, so there's something wrong with the connection refused. Is my accept handler not working? Did I pass the wrong socket? EV failed to read. Yeah, that's correct.
You giving it knee-high socks, and we're expecting ankle socks.
Yeah, I'm giving it a lot of socks, huh? I'm a little bit confused why this is not working. Except ready event, yeah, that makes sense. Into the worker routine, waiting for event. Um, maybe I need EV enable on this. Let me build it once again. No, it just doesn't go past that. Let me see if I even get events to begin with. So if I see here, stud print ln got event. Let's just say if I get an event. Now, this is the annoying part of working with system calls. You have to debug it sometimes. No event. Interesting. I don't even get an event. And my accept ready event just so incorrect? I think it's correct, no?
Looks right to me.
It looks fine to me too, that's the worst. So clearly it does get to waiting for an event, and then the event never occurs, huh?
Uh,
Are we sure we're binding to the correct address? Yep, 420, 69. I am really confused about what I'm doing wrong here. Oh, did I forget the listen call? Oh, I forgot to listen. Oh my god, what an idiot. I forgot to listen.
mm,
I can't accept connections without listening on them. Bruh. I can copy paste that um, from the previous program. I'm just gonna. Um, so obviously that's not gonna work. I forgot to listen. Oops. Um,
Oop.
yeah, oops. That's a classic mistake. I forgot to listen. Listen to your operating system. It's a good advice. There we go.
Why are
Let's
men?
hope that this fixes
Why are
it.
programmers not good listeners?
No idea. Let's see. Let's go to build. Let's make it and let's run it. It's waiting for an event again. Let's see if I can open a terminal and telnet here once again. We got telnet localhost. Was it 42069? Hey, I forgot the new line once again.
Yay
All
for
right, all
new.
right, all right.
Yay for new lines.
Yay for new lines. Run it once again, and now I'm gonna telnet into it from Linux. And hello, mom from FreeBSD. Boom! That's the asynchronous FreeBSD web server written from system calls with no libraries. Ta-da!
Hell yeah.
In 99 minutes. I didn't even need 100 minutes to do it.
That's hilarious.
Hilarious. It's amazing. Oh my god, I need a break, bro. Isn't that cool?
That is actually pretty cool.
Yeah. Let me actually build this for release, huh?
Yes, make sure to throw that
Build
up
for
on there.
release, rebuild it. Make sure I didn't cause some undefined behavior. Wait, I don't need this. Um, telnet back into there. And hi, mom from FreeBSD. Yay! There we go. And it gets the event, it handles the event, and it's working beautiful. You know what would be even more fun? Is if I, let me get that, let me see. So first of all, I need to I have a bunch of terminals here, which I didn't close. You know, it would be fun if I did strace. Let me actually. Oh, I don't have strace installed here on this FreeBSD installation. Oops. Hold on a second. Let me log into root. pkg install strace. I don't have strace. Okay, well, we'll forget about it then. We'll do strace on Linux. Anyway, so this is the web server. So, and I did it with Telnet here to demonstrate it, but now let's actually write a client, and the client I'm gonna write on Linux with IO Uring. Okay, so take a step back, get another coffee because it's about to get even more real with some IO Uring. Let's get it. Document CPP midnight IO Uring. There we go. So first let's make a sync client, and then we'll do the async, the IO Uring client. So the sync client again is just for us to understand what sort of system calls we're going to be making. And once again, it's not that different to what we've been seeing so far. Let me just cpp cmake. Let me copy over a good cmake list.txt source and build directory. So the cmake lists file, I'm just going to yoink the same template as so far. It's been working nicely. And the project is the sync client, and everything else is going to be the same. Okay, nice. Let me just test my Linux to make sure it actually works. Include print main std println hello world. Don't worry that it's complaining. It's because I have not updated the I didn't make. Oh, okay. Wait. It's because I haven't updated the compilation database, which I'm gonna do right now. So let's go into build. Let's cmake with the cmake build type equals debug. And since I'm on Linux, there's actually GCC and Clang here. I specifically want Clang.
Clang.
Yeah, the reason for Clang is because the LSP understands the compiler feedback of Clang better. So when compiling, I'm going to compile with both to make sure both work for compatibility reasons. But when developing, it's much easier to deal with Clang because the LSP understands Clang better than GCC. Anyways, let's make it, run it, and there we go. So I'm going to take the address. Wait, let's format that. I'm going to take the address which we're going to connect to from the command line arguments. And the command line arguments in C are, so in Java they're passed as a string array, right? So public static void main string array args. So the string array is here, and the length of the string array is here. So in C, or on Linux in general, the arguments passed to your executable are first the path to the executable, so the path to yourself, and then the user provided argument. So I want a IP and a port from the user. That means two user provided arguments plus the path of the executable. So I want in total 3 arguments. So if the number of arguments is not 3, we're going to print out println usage client address port. There we go. And return exit failure, because I don't know what to do. Now we're going to do mostly the same stuff as before. Once again, I want to get address info. This time I'm going to get address info of the address which the user provided. So let's first get a hints and results variable. I need to include something for adder info. Let me just make sure to check the man page of get adder info. The man page says I need D3 includes, which I can yoink from right here. And there we go. Now I'm gonna copy from the FreeBSD implementation basically the same get adder info call in status get adder info. The name is going to be the argv1, so the IP address which is passed by the user. And the port is going to be argv2, the port which is passed to the user. I'm going to use the hints which I specified here. So I want any IP family, so it, IPv4 or IPv6, I don't matter, and I want a TCP connection. And I'm going to pass its result. So I need if status is less than 0, that means that I cannot resolve address. Let's put the address here. Error, and then put the error here. So the address is argv1. The error is errno and stir error errno. There we go. Return exit failure. If I can't resolve the address, I cannot connect to anything. If I do know what the address is, then we can start to cook. Oh, by the way, I forgot we need a deleter, so let's get a unique pointer again to adder info with the deleter type being this lambda, which takes an adder info pointer and just calls free adder info of info. There we go. Clean up adder info of result. There we go. That's the memory management for that object done. Now, instead of accepting connections, we are going to be the ones initiating the connection this time. So we are now from the other side of that bilateral relationship. But still, we need a socket. We need socks. So let's start by getting a sock. Hell yeah, we need socks. So in sockfd, let's get my sock over here.
Go get a drink of water. Fill up my bottle here, right quick.
Let's socket. And thanks to our getAdder info call, we can just pass the info which we got from that call. It's so nice. I don't know why people keep manually filling this out when there's a C library function to do it for them.
Rock'em sock'em robots.
There we go. So if the sock fd is less than 0, then we have an error to print on. Again, without socks, there ain't no luck. So we absolutely need socks, and no socks means no program.
No socks, no service.
So, yeah, no socks, no service. Exactly. So let me just log the error and stir error note and return exit failure. Now, otherwise, we do want to clean up the sock whenever we're done with it. Although, I mean, this is the only socket we're going to use. We don't need to. The kernel will take care of this. Of course, we're going to use only one socket ever. Anyway, so now we're interested in the connect system call, which actually initiates the connection. The connect system call connects the sock referred to by the file descriptor to the address specified by address. The address length specifies the length of the address. All right, so now we can actually connect. So this is again a fallible function, so let's get the status of it. I'm going to connect to the sockfd, to the sock file descriptor, the result address with the results AI adderlen. Again, this is the information we got from getAdder info. Very nice C library helping us get all the info we need. So that's what we are reusing here instead of manually filling it out. If the status is less than 0, then the connection failed. So again, you may want to retry it, but here I'm just going to bail out and return exit failure. Otherwise, the connection was successful. So the sockfd is now connected to the address which we specified. Just check the return, just to make sure. Right, so if the connection succeeds, then 0 is returned, otherwise -1 is returned. All right, there we go. So connection, if it succeeds, then we can just read from it. So let's Get ourselves a buffer of, let's say, 1024 elements, all initialized to 0.
Sorry.
So if, and then let's just read from the sockfd into buffer 1023 bytes. We want to keep one null terminator at the end, and std print ln. So actually, first of all, I need to check if the read count is less than 0. Read count less than 0, right? Because if we check the man pages for what? Buffer delete. And check the main man pages for read, we see that it returns. Oh, that's the wrong read. I mean man2 read, the system call read. Returns. The return value is the number of bytes read or -1. So if it's less than 0, std print ln error reading. And let's just post the error. And return exit failure. Otherwise, I'm going to print ln read and then the message buffer. So that's the client already done, I think. Let's go ahead and build it, make it, and I made a mistake. I didn't save it after I edited. Make it, run it. Oh, I forgot to run it actually with the correct. See, that's a helpful error message, by the way. Usage client address port. All right. So there we go. That's telling me the address. So main, and the port is, I actually need this to be running, by the way. Holy shit, I forgot it needs to be running. Let me start. So here's the FreeBSD virtual machine once again. I'm going to start the server running, and I'm going to connect to the port 42069. And we read Hello Mom from FreeBSD on Linux, synchronous. Yes, that is a TCP client.
Hell yeah.
Hell yeah. And now
Hell
the
yeah.
last thing we're going to do is going to make it asynchronous. Because this is a blocking read. Once again, it blocks. It blocks for the entire duration of the internet connection, which could be across the ocean. And we want to do this asynchronously.
Yeah, we must block
This is,
that one.
but we got this in the synchronous fashion. By the way, if you want to know what I'm going to ask you to write in Java, it's exactly this, but with virtual threads, because virtual threads are Java's version of async. But this is what you're going to be writing. It's very simple.
We're gonna see if we have time for me to write it, cause like we're cooking up on 2 hours.
Yeah, well, there's still IO Uring which needs to be handled. So let's take a look here. Just a second.
We might get to the Java.
And we might get to the job. All right, let's get to the IO Uring for sure. So let me make a cmake list.txt, a source, and a build directory once again. Let's change over there. And now let me explain something. So IO Uring, or as I like to call it, AO Uring.
Heyo.
Yeah.
Mm.
So it's a Linux specific system call API for asynchronous IO. And basically the way it works is you have two ring buffers, so circular buffers, where in one buffer, your program puts submission requests. So we put our request object in the submission queue, and then the kernel at the same time reads our memory. It peeks into our live memory and checks for all the submissions we have submitted. And as we go along submitting them, the kernel immediately, without any notification from us, well, some notification from us, but in the best case, without any notification to us, gets to work and immediately handles the IO in the background. So we make requests, we put them on this ring, the kernel chases after us, and whenever the kernel is done, the kernel then puts its completions on the completion ring on the other side. And then we take the completions from the completion ring. All of this is without any system cost and merely accomplished through mapping a shared page of memory with the kernel. So we need to mmap two pages, basically one page for the submission queue and one page for the completion queue. And these maps need to be shared memory. We're basically doing inter-process communication with the Linux kernel here. So if you
Okay.
take a look at the man pages of IO Uring, you'll see that these request structures, so here you go, the struct IO Uring submission queue entry, are absolutely massive and very, very difficult to deal with. So once again, we need to mmap. So if we search here for mmap, you'll see that this example here requires the use of at least two mmap calls. In modern Linux version, just one. Now, to avoid dealing with this manual mapping and manual process, again, there's two processes, so we need to synchronize across processes, which is very dangerous and very difficult to manage properly. There is actually a library which Linux recommends us to use. So it's in the man pages for Linux, and it's confusingly under IO Uring setup, I think. Yeah, so the Linux man pages point you to liburing. And if you search for it, liburing, it's this library here, which is a small and very, very thin wrapper around IO Uring, which just deals with the pointer arithmetic and the memory mapping for us. So we don't have to deal with the extremely unsafe and risky operations. Right? Because if we mess up any of that, an immediate crash to a program or a critical security exploit. So I really don't want that. I think the best thing we can do is simply use this liburing library, because it's a very, very thin wrapper around IO Uring, and it's still perfectly low level enough. And in the end, we're going to end up calling the exact same system calls anyways. So there's literally no difference. Why is this not doing what they wanted to do? So to get this library, I'm going to use a C++ package manager, which is VCPKG. It's by Microsoft, sorry. But it works, and I can add the liburing as a dependency right there. I need to actually deal with telling CMake now that we are using VCPKG, and that can be accomplished using a CMake presets file. I'm going to copy paste over a CMake presets file provided by Microsoft. Once again, this just basically defines a preset called VCPKG, which tells CMake, please use the package manager. All right, now that we have installed liburing, we can now write our CMake list.txt, which is going to be almost identical to the previous one. I'm going to just copy it over. It's now going to be the IO Uring client. And the one difference is that now we actually want to link the library against liburing. We want to actually use it. This can be accomplished with the following three CMake commands. So I'm going to use the find package config module to just find the package liburing, which is going to be provided by VCPKG. And then I'm going to target link libraries. I'm going to link to the main target what package config finds for liburing. By the way, liburing is so popular and it's so heavily recommended to use it. Almost every Linux distro actually has it in its package manager, including the full source code. So really, I'm using a very, very shallow layer here to just avoid dealing with mmap, which is very dangerous. And also the reason IO Uring caused like 1,000 CVEs in the Linux kernel over its history. So much so that some distros disable it in the paranoia that it's going to blow up somehow. I'm going to explain the security concern behind IO using in a sec here, but let's actually get to using it. Once again, let's test out my compiler, just make sure that everything works, that the build system is configured correctly. Of course, it's going to complain for a sec here until I actually get the compile command ready. Going to use this vcpkg preset, which I just set up. So that's going to tell the package manager to go out and install LibUring to me. And once that's done, I can just build it with the Ninja build tool and it works. Okay, perfect. There we go. Now we can kick it off. So the starting bit of our asynchronous client is just exactly the same as the starting bit of the synchronous client. It's all the same. We need a socket and we need some address info. So I'm just going to copy paste it over. I'm going to need some of the include files. Let me just copy paste them over too. There we go.
Happy.
Make everything happy indeed. Now we get to the connect system call, which is the first blocking one. All right. So this is where now we're gonna need to use the facilities of IOUring to allow us to do the stuff asynchronous. So first of all, we need to actually set up the ring. So let's first of all, let's include liburing. It's a single header file. And I want an IO ring, the actual ring itself, and I'm going to call it IO ring as a global variable. The number of entries in that variable, I'm going to just set them to, I don't know, like 124. It's plenty of variables. And after we've connected to the socket and all, we can now deal with setting up the IO ring. Do I do that first? Yeah, let's do that first. So before doing anything, let's set up the IOUing. So for that, let me get the manual pages to that. We need the IOUing queue init library function. And this function is the one which does the memory mapping for us. We don't have to deal with it. So let me just mention here in this manual page, which you can see right now, we need to pass IOUing the number of entries we want, the actual ring, and some flags. Now the flags here are really exciting. There is a lot of possible flags. And depending on which ones you pick, the kernel will be behaving differently. So one of the most interesting ones is the IOUring setup poll, which tells the kernel, whenever I submit entries, so I submit requests, it's very likely that I'm going to submit more. So it's not going to be one by one, it's going to be a lot of requests quickly. And the kernel is going to set up a thread which repeatedly polls the submission queue without any system calls, which just polls the submission queue and checks whether we have submitted anything into it. And if we have, it's immediately going to get to it. So think about this. We can tell the kernel to do work without ever actually using a system call. Isn't that crazy? We never need to switch the privilege level of the processor to kernel mode to actually use the kernel. This is the thing which I believe is only possible on Linux with IOUing. It's such a novel thing. It was, as I said, introduced in 2017, the first version. And it's for the first time that we can get the kernel to work without actually switching into the kernel ourselves.
Interesting. That is interesting.
Right, so that's very interesting and also very performant because, like CPUs have a lot of speed gains from speculative execution. They execute more than one instruction at a time. They prefetch memory, they prefetch pointers. They do a lot of things at the same time. But this behavior of CPUs makes them prone to so-called meltdown attacks. And if the context switch between userland and kernel happens too quickly, you could guess and read kernel memory just by measuring the timing of the system call. So every single modern kernel makes many protections against that by forcing the CPU to flush all of its caches before actually entering kernel mode. But that imposes quite a notable performance penalty. With IO we never make a system call and we never need to deal with that performance penalty. And the kernel will just go off and work, and no performance penalty will incur at any point. That's the power of inter-process communication with the Linux kernel itself. If you want to make the most performant and efficient I/O program possible, you're gonna need to read all of the possible flags for the configuration of the kernel here, and make sure to pick the right ones, because that can have a significant impact on how helpful or even unhelpful I/O Uring is. Now, for demonstration purposes, I'm not gonna touch these flags. I'm just gonna use the default no flags. But you really should take your time to read about it if you're interested in high performance I/O on Linux, and it can get really, really scaringly fast. So I/O Uring queue init is what we want.
Strap yourself into the fucking jet, and let's get going.
Yes, sir. So I'm not gonna pass any flags here. I'm gonna pass a pointer to the I/O ring, and let's take a look at the return value. So this is a fallible function. Now, since this actually boils down to a system call, I need you to think about it. So system calls do not have access to the error_no variable, because the kernel doesn't know where my error_no lives, so it can't write in there. So what the kernel does in its system calls is, in case of success, it returns a positive number, and in case of failure, it returns minus the error number. So that's the case here too. So we still need to check whether status is less than 0, but the error code now is actually minus status. So std println, if I cannot get the ring, I cannot live. So I'm gonna panic here. Cannot set up IO Uring, and let's just pass the error number and the explanation. So the error number, once again, is minus status, and that's what I'm gonna pass here. Return exit failure once again if that doesn't work. So at this point, the IO Uring queue is successfully initialized, and we can actually get to it.
So now, if the
So once again,
status is less than 0, do you have to explicitly say that it's a negative status rather than
right.
just
So you're right. So I cannot use error_no here because the system call doesn't actually know how
no
to
no
set error_no.
can't you just use status? Like you have to explicitly say negative status?
Right, because the statuses have meanings which are encoded by the error number. So if I open up I don't know what's up with this Vim, why the shell keeps not shelling, but if I check man error_no, you can see that there's a lot of possible error number values. See, and they all mean something. So you're gonna get the specific meaning of whatever error occurred as minus the status returned.
Okay.
So for example, default if I pass a bad address. So those are reserved values. That's why I use it, just to know what actually went wrong. Okay, so once again, we're gonna make a worker routine, right? Void worker routine. That's what we're gonna be doing to handle the asynchronous requests. So that's what I'm just gonna call here. First of all, we need to submit a connect request, right? So if we check over to the synchronous client, what did we do after getting our sock? We connected to the sock. So we now need a connect request. Okay. Let's get a man Uring enter. That's the system call behind all of it. And now I can look for the connect system call. Uring operation connect. Issue the equivalent of a connect system call. That's what I want. I want a connect system call. So I'm gonna get a submission queue entry. So IO Uring submission queue entry. My submission queue entry. That's gonna be a pointer. You'll see why. So I'm gonna get the address of a submission queue entry in the IO Uring. I want to get a submission queue entry from the ring, IO ring. So this will populate this variable with the address of a submission queue entry from this IO ring. It will, if the IO ring is full and the kernel is being massively late, this will block, by the way. So the IO ring is a limited size ring buffer, and this will wait for the kernel to be done with something. But I mean, I put 1,000 spaces in the ring, so I don't think it's going to be getting full anytime soon. So this is basically not blocking. Anyway, I want to prep the connect system call. This is the submission queue entry. Actually, it's already a pointer. Which file descriptor are we connecting to? It's the sock. We need the sock address. Just a sec.
My God, there are so many socks.
There's so many socks, am I right? Oh, by the way, I'm slightly tripping. I made a mistake. Turns out we could do even this call asynchronously. Shit! Let's do that asynchronously too. I want to get the socket asynchronously. I completely forgot that. Let's take a look at the man page just to make sure I know actually what I'm typing in there. So man IO prep socket. So here we have to get the domain. So that's where we use the information we got from getAddr. It's going to be a TCP socket. Info result, the result information, flags, and finally the last flag, which I don't care about, is going to be 0. Right, so it's going to prepare a socket request. Now, we need, again, a handler to handle the completion when it arrives. So at this point, it may make sense to take a look at IO Uring once again, and let's look at the completion queue entry. Struct, yeah, there we go. That's the submission queue entry. It has a bunch of stuff. Now we want the completion queue entry. The completion queue entry is much simpler. It contains, again, another 64 bits of user data, just like in KQ. Once again, we have the opportunity to pass 64 bits of user data through the kernel unmodified. So once again, I'm going to use that to polymorphically determine what the correct handler is. Let's get that done once again. So an interface, a handler interface is what we need. Virtual void handle yourself, which is abstract. There we go, a semicolon here. And first of all, I need a socket handler, sock handler. Haha! It's gonna inherit from the handler, and it's gonna be the continuation to the socket request. So let's actually just put that right there. Let's make a sock handler, socket handler, the new sock handler. It's a pointer. And then I'm gonna IO Uring set data. So I'm gonna set the the user provided data to the socket handler. And then we're gonna do IO Uring submit. We're gonna submit our request, which we have prepared in this IO Uring. So that means in our worker routine, we can now make the same loop as we did last time. So while true, we need to wait for completion queue entry. So for that, we're going to use IO ring wait completion queue entry from the IO ring. And I need a IO ring completion queue entry pointer, completed entry. So that pointer is what I'm going to pass over to the wait for completion queue entry. By the way, this is another fallible function.
Mm.
Oh my. Yeah, we need to check even more return codes here. Man, using waits completion queue entry. So this is once again this problem with the negative status, because this relies on system calls, and system calls do not actually change the error node number. Instead, print ln error waiting for completion queue entry. So minus status is the error number, and error of minus status is the message. We're going to return. Can't deal with this. I mean, we should be able to wait for a completion queue entry. The only cases where it doesn't work is like when we're out of resources or something disastrous has happened. Mind you, this will not fail if the request itself fails. If the request itself fails, we're going to get a valid completion queue entry which just contains the error inside of it. Okay? This failing means that the system is unable to deal with the memory load of the completion queue, for example. So that's a really very, very difficult error to deal with. This is why I'm just bailing out in the case of this particular error. In any case, by the time we have waited for this completion queue, we now actually have our completion queue entry, and I'm actually going to copy it over to next entry because I want to advance. I want to tell the kernel I am done with an entry, or however many entries I am. And that frees up space in the IO during completion queue for next completions. And I'm going to advance it by 1. IO during, not buffering advance. What did I do? Oh, sorry, not the completion queue needs to advance. There we go. Forgot the function name for a second. My bad. This is an infallible function because remember, advancing the completion queue only amounts to moving a single pointer by 1. It's the magic of memory mapping and interprocess communication. This just cannot go wrong, so this returns void, and we have advanced. Thankfully, though, while this pointer is now no longer valid because now it points past where we've advanced, we have a copy of the completion queue entry right here. And by the way, I forgot about handle yourself, but we want to pass the completion queue entry to handle yourself as well. So this should take a IO during completion queue entry, my CQE. That's so that the handler knows what it's dealing with. Right, so then we're going to be passing the user data as the pointer to the continuation. So if that is equal to null pointer or 0, we're just going to continue. It means nothing here. I'm going to just log it for a second. No data in completion queue entry, sus. Sussy baka kernel. Anyways, if we have done that successfully, then we can cast to a handler pointer because we are sure this is a handler pointer. Handler is a reinterpret. I think I can even get data. No, I just need to cast next entry dot user data, which is I know is a pointer because I set it to 1. I'm gonna unsafely reinterpret cast because again the kernel doesn't know this, but I do. I know this is a valid pointer at this point. And handle yourself with the address of the next entry. And there we go. So that's again the very simple event loop, which is just gonna wait for completion queue entries and call the corresponding handlers. Okay, so now time for the socket handler. Let me just take a look at my notes to make sure I don't screw it up too badly. All right, so if we look at, so notice a difference between KQ and IOUring. So KQ only tells me when I am ready to do something, whereas IOUring actually finishes the job and gives me the results back. You see how that's very different between the two OSs?
Yeah. Yes, that is.
So IOUring actually does the work, whereas KQ would be like, you do it.
Sounds like a government.
Yeah, sounds like a skill issue, huh? In any case, let me just exit here. Buffer delete. So, the socket handler. So we need to, so once socket connection is actually successful, the next thing is to actually connect to the socket, right? So the socket handler needs to connect. The first thing is we're gonna use the little unique pointer trick to clean ourselves up. Oh, I forgot to see there the warning on forgetting to mark the destructor as virtual. There we go. That's the cleanup here. So let's take a look. So this is on the socket entry. Okay, so let me just close it. Let's actually open a new terminal. Let's look at man IOUring enter. And let's look at the operations. Let me just zoom in a little bit. So socket. IOUring up. It issued the equivalent of the socket system call. We just read about that. Let's see what it returns. Is there anything? Actually, what we need to look at is man IOUring and struct IOUring CQE. Yeah, so result code is, so in the result value, we get the actual status of the system call. So the status of the socket command is in the myCQE dot result variable. So now what we need to do is look at the socket system call and see that it returns the new sock or an error. So if status is less than 0, then we have an error. Still print ln socket failed, no socks.
Knock your socks off.
Yeah, we got our socks knocked off. Again, this is the system calls we're dealing with, so it's the negative of the error which gets delivered to us. And in this case, we really can't do anything. I'm just going to return. Otherwise, the int sockfd, so the socket file descriptor, is equal to the status. I mean, we don't technically need this variable, but let's just make it clear to ourselves that the status is the sockfd, the new file descriptor. So the next thing we want to do is connect. So that's why we're going to do IOUring prep connect. So I need a submission queue entry for that. So first I'm going to do IOUring get submission queue entry from the IOUring. That returns an IOUring submission queue entry pointer, my submission queue entry. so not the same as the completion queue entry. We pass that in here. The file descriptor which we are connecting to is the sock descriptor, sockfd. Now, the address we need to know, so I'm going to add a field here, which is a sock adder address, connect to address. That's going to be here, and the connect to length. So we're going to get that passed from the outside. What did I do? Oh, I need to do this with pointers, right? What did I do?
Is it pointers? No, one's a pointer, isn't it?
Oh, it's one of the pointers. The other one is not a pointer. Oops. What did I do now?
Isn't that only? Doesn't that?
Yeah,
Is the file sock file? Is that supposed to be? No.
Yeah, the sock file descriptor is a integer. That's correct. I need a sock adder. That's also correct. And a socklen. Did I just not save something?
What's the
Oh
sock?
yeah, it's a typo. Sorry, it's not a completion queue entry. I need a submission queue entry. Oops. Maybe I should rename this to something my submission. Let's make it more obviously different. Yeah. Oops.
Fucking acronyms.
Yeah. Goddamn acronym. So by the way, now that we know this, we can make the constructor of this so that we can actually call it downstairs. So let's say sockadder address. It's incoming address. Let's say connect to address. And a socklen connect to length. And I'm just going to initialize the two value. Oh, there you go. That's it. And now downstairs here, I can put the variables. So where did I? Yeah, so the address. So result.ai adder and result AI length. So this, by the way, needs to be a pointer. Let's just make sure that it is. And that is a pointer too. Connect to address then is a pointer itself. I don't need.
Yes,
What?
you do.
It's a contract. Connect to address is the socket point. Oh, pointer, please. That was a reference, my bad. Yeah, that's well the reference. I need a pointer here. And that's because I want to pass the pointer to this to the sock handler. There we go. That's the correct handler. Now the handler gets filled up with the correct info. That's really good. Let me just make sure I did it correctly. Checking my notes again for a sec. Yeah, that's correct. Elder and elder. That's what we want. Perfect. So now we need to deal with the connect handler. Right? So let's make a struct. Right, so here we stopped here because we need a connect handler now to do right connect handler. So that's what we're gonna do. It's gonna inherit from handler again, and it's gonna have void handle yourself. Your completion queue entry, my completion queue entry. Override. There we go.
Don't forget your hand. Your oh, never mind. A virtual handler is already up top. Never mind. Never mind. Keep going. You're good.
Yeah, I did put the virtual destructor in there. Though what I did forget is socks again, because we need to know which socket we are connecting to. That's a lot of socks, and we're not even writing Rust yet. Imagine when we get to Rust, huh?
I've never actually written Rust, so I don't actually know what I don't know. I don't know the syntax of Rust. I don't know anything about it.
You should Google the stereotypical Rust user uh,
We'll have to see.
aesthetic.
We'll have to see if we can find a somebody that's like a quote expert in Rust and see if you and I can interview them next week.
Yeah, I do have a candidate, though he is a little bit ecstatic about Rust, but in my opinion, in a positive way.
Well, I mean, if he's an expert in it, then I'd be curious to get him on here and see if he'd be interested to chat. But
I think so. I hope so.
I know nothing about Rust, so it'd be like with C.
Yeah.
At least I've touched C in my younger years. Rust, I've never looked at it. I've never written it. I've It'd be interesting to find out about what the hell
Yeah.
exactly it is.
All right.
That's
So once again, the result of the connect request is going to be in result. Let's then look at man connect and what it returns. Return. Return, please. Um, right, so it's just whether it's success. So if it's less than 0, it's failed. If it's more than 0, it's success. So again, if it's less than 0, std println connection failed. And let's just report the error. MySQL.result. And it's a negative once again. And a stir error of minus MySQL result. There you go. That's a typo. Nice. And in this case, we return and nothing else. Okay. So if this connection actually works, we need to read. So we're going to need a read handler. By the way, now that the connection handler is written, we can actually use it here. Let's make a connection handler. Connection handler equals, that should be a pointer, new connect handler. And we need to give it the socket. So socket D here. IO set SQE set data on my submission. We need to set the data to be the connection handler. There we go. And we just gonna IO submit with the IO in here. And that's about it.
now.
So,
I do
yeah,
just want to point. I do want to point out that we are at the just over the 2.5 hour mark. If
yeah,
how much?
we just need the read handler and we're almost done.
Alrighty.
We are indeed on time. Let me
I,
just write the read handler. Once again, I'm gonna try and do it as quickly as possible.
yeah, I don't want to rush you on this, but I do need to
Yeah,
talk
it's
about some.
one more handler which we need, which is the read handler just to actually read, and then we're done. So the
Alrighty.
read handler, by the way, needs a buffer. I'm gonna say 124 elements. I'm gonna make a convenience function which just tells us how much to read. That's a constant function, meaning it does not affect the value of any member fields. That's how much we want to read. So this is, by the way, so the connection handler, once we have connected, we want to read. So here we have a to-do read. We're going to pack a submission queue entry into there. For now, let's see how we handle the actual reading. Once again, the same unique pointer trick to delete myself
All right.
at the end of the function.
I just need a quick minute. I'll be back in just a second.
Sure.
Feel free to keep going. Don't worry. Don't worry about me.
Yeah, I'm going to keep going. If the result is once again, less than 0. That means that we cannot read std println, read failure. And I'm gonna basically copy over this whole thing. There we go. And return in that case. Otherwise, we're gonna say std println read how many bytes. That's the result. And let's actually print the message we've gotten. I'm going to put a new line before the message and put the buffer here. Now we need to deal with the constructor a little bit carefully here. Let's actually initialize this to 0 by default. Exactly. So now that we have connected, we want to initialize a read. Let's finally look at Prof delete terminal man read. Let's see how we can use read. That's the wrong man page. I need man to read. There we go. Size T read. So we need to read from file descriptor, buffer, and count. So IO. So we need a submission queue entry again. When IO using submission queue entry pointer, my the next submission is IO using get submission queue entry from the IO ring. If we can, once we get the submission queue entry, we need to IO using prep read. The submission queue entry is the submission. The file descriptor is the socket file descriptor of this particular object. The buffer. So the buffer is going to be the buffer of the read handler. Let's actually make a read handler that does not take any constructor arguments. We're just going to put here read handler's buffer. How many bytes we want to read, that we are going to get that from the read handler read count function. And the offset is going to be 0. We want to read from the start. During SQE set data, we want to set the data of the submission to the read handler, once again, because the data should handle it, and IO during submit everything in the IO ring. There we go. I think that's it. With any hope, I am probably done. Let's just make sure I am actually done. So let me get a new terminal here. Term. Going to build. Build it. Let's hope I don't have any errors. I don't. Let's connect. And I got the message asynchronously. Hello, mom from FreeBSD with the Linux asynchronous client. I am done. My async program works, and it's basically jailbroken. Let's try it with strace just once to make sure that we are actually calling IO ring enter. There we go. So there are your IO ring system calls. Now here we could actually even play around with the IO ring polling mode. Let's say IO ring
Poly mode.
poll.
Oh, poll mode.
Polling. Yeah, poll mode. IO ring poll. Let me. I forget how the flags work. Man IO ring flag. Man IO ring setup. Let me just look at IO ring setup IO poll. There we go. That's what we want. IO ring setup IO poll. So we want the kernel to poll. Let's rebuild that. In the terminal here, cd to build Ninja And now let's actually S-trace this so that we can see the system calls. Okay, that's a lot of system calls. IO using enter. Not what I wanted. So we don't want polling here. Forget about that. We most definitely do not want polling. Let's S-trace it. There we go. You see the IO during enter system calls, which tells the kernel, do work. Do everything I told you.
And then it's reading the bytes down lower.
Right. Don't worry about this, right? By the way, the socket, the file descriptor 1 is the standard output, and writing to standard output doesn't block.
Okay.
Yeah. But, ta-da! It works! We get Hello Mom from FreeBSD. It works. The asynchronous Linux client actually works.
Hell yeah.
So if I now just run it without... Oh. There you go. See, it worked. And mind you, the FreeBSD thing is recording that it got a bunch of connection events. Isn't that nice?
I see that.
Yeah. So
Nice.
we have effectively connected FreeBSD and Linux via the TCP internet, and we have succeeded to say hello mom from FreeBSD, asynchronously sent, asynchronously received, connected to completely different operating systems. That was epic. I think that was epic. Don't you think that was epic?
I think that's pretty impressive.
Now, a few closing remarks here before I let the people go. The stuff I posted on GitHub actually makes some sense. So, let's just take a look at it together. If you want to learn about the low-level details of networking, the best guide I've found ever is BJ's Guide to Network Programming using sockets. So, sock tutorial. There's your HTML, and there are all the system calls which I used. You can learn all about them right here. Obviously, make sure to use man pages. The man pages are your best friend. And if you don't have access to a terminal right now, there's Linux man pages on the internet here, man7.org. And FreeBSD man pages are here, hosted by FreeBSD themselves. So you can get information on every single system call in the second category. Once again, the most important man page is the man page about man pages, which tells you where all the information is hidden in your system. Did you know, by the way, Windows Vista is the last Windows version to contain manual pages built into the system. After that, they moved the Windows API documentation to the internet and it doesn't come with Windows anymore. Sad.
That's an interesting fact.
Yep. You need to Google Windows API documentation. There are no man pages for it built into the system anymore. But if you're dealing with syscalls, this is what you want. Again, what I did is compatible with FreeBSD, OpenBSD, macOS, and Linux thing I did is compatible with Linux, obviously, and unfortunately only Linux. Now, for those of you wondering, FreeBSD does have a Linux compatibility mode. However, they did not re-implement IO-Uring. So if you load a Linux executable which uses IO-Uring on FreeBSD, every single IO-Uring system call is going to fail. So it's not going to work. That's, by the way, one of the reasons we always check the failure conditions, because someone might be running this in basically an emulated environment where the IO-Uring calls are not implemented. Next thing I want to tell people is check out liburing. It's the best way to use IO-Uring. It's what I did today, and it's very easy to get used to. Unfortunately, their documentation is pretty poop, but for some reason they have man pages on absolutely everything. If you start with IO-Uring Q init and start reading here, you can get to all you need to do to completely use IO-Uring end-to-end. So I highly recommend reading the manual pages, and it's so nice that this library comes with complete manual pages. Okay, next libkq. This is if you're interested in writing using the KQ API on Linux or on Windows. I do want to point out something which may be a future stream idea, also something which is a great continuation on this stream. You should take a look at Soding, learning about one of the biggest, let's say, gotchas in network programming, where TCP, the transmission control protocol, which is meant to be reliable, is not as reliable as you think. And Soding very nicely explains why it's not.
Huh.
For those interested in some measurements on how I/O urine performs, check out this paper or this one. And finally, for a Java reference, the base JVM does not use I/O urine. I guess they were concerned about security implications, but NetIO does. So if you write a Netty client, which I'm wholeheartedly inviting you to do in a stream yourself, maybe, so that we can connect it to a FreeBSD server, then this would use I/O urine on Linux and the correct implementation on the correct operating system. So not, the
Might have
Java standard library doesn't do that.
we might have to do a follow up on that one on one of our future streams together.
Yeah, I mean, you could show me a bunch of Java here. We could continue on with that. And we left out Windows here, but I think that's a good thing considering how long we've been going. Yeah. Windows is the oldest one, and it really hurts me to see how Minisoft have ruined their perfectly good operating system. I just can't believe that they had like the most brightest people in America collected at Microsoft writing a actually decent operating system, and then they screwed it all up. It's like the most legendary failure of failures.
This is why you
But
don't let
anyways,
AI run your company.
yes, this is why you don't let AI run your company. But like just to give you an example, so the IOCP is the Windows asynchronous API. It was released in Windows NT.
Oh wow, that it was that
So
long ago.
Windows NT 3.5 and later. Let's see, Windows NT 3.5 release date. 1994, the first one.
That's why I said that was that long ago. Like I was impressed. NT was very long ago. That's an old ass
Yeah,
system.
well, all of the Windowses are still based on NT, even Windows 11.
Yeah, like my first experience with Windows was a Windows 95.
Oh, you were even before Win NT. Wow.
Mm, yeah, that was my first experience. My family got a Windows
Yeah.
95 computer back in 1997,
Yeah.
and then I was addicted to pinball.
Pinball. Ah, yes, the good old times.
Good old little pinball machine. I was addicted to that, and then I got curious towards how the computer worked and why it was different than a TV,
Yeah.
and then that led me down the rabbit hole of tech.
Yeah, I mean, I can show you something which is a little bit interesting, I think, um, which is if you go into, oh, I'm not authorized to do that. Never mind. If you go into Windows, you can still find the old NT kernel inside of Windows as the actual kernel of the operating system. Anyway, so Windows was the first with actual genuine asynchronous I/O. And then BSD, very shortly after, followed with KQ. And then Linux is very late with 2017. And like this lateness of Linux and people's obsession with Linux combined to create a lot of incorrect opinions on the internet. Like, for example, people believing that stuff like disk I/O is necessarily blocking. You see claims like disk I/O is inherently blocking. So if you look at the FreeBSD man page here. So let me cancel the server here. Let's go man AIO read. So AIO is asynchronous IO read for specifically files. So if we take a look here. Let me just see. Or maybe. Oh, sorry, not that. Wrong man page. Man AIO, just AIO. There you go. So asynchronous I/O requests to raw disks are queued directly to the disk device layer after temporarily wiring the user pages. So basically, what the kernel does is it allocates virtual memory for the thing you're about to read. It maps the virtual memory,
Hmm.
and it tells the disk, the controller, go do your thing, and completely abandons the operation while it's in progress. It gets
Wow.
notified by the disk controller when it's done.
Huh.
So most importantly, this request is not serviced by any of the threads in the AIO daemon pool. So people know IO is not inherently blocking, and what I wrote today shows that.
Hmm. Wow. Now,
Any questions?
before we wrap things up, I was just gonna say before we wrap things up, does any of our viewers have any questions, or Prof, do you have anything else you wanna add?
That's all I got for you today. It was a very, very intense stream, I think. We
I think
wrote
that
four
I think
programs, two synchronous ones, two asynchronous ones. We were lucky enough that all of them worked. We learned something about the system calls for networking, for TCP networking. And
Hmm, I
we
think this
even
was
learned about asynchronous IO.
I think this was quite the good stream, and if you guys watching at home think it was a great stream, then leave us a like. And if you want to be notified when we start up next week, by all means, smash that subscribe button, turn on notifications, and get notified when the Dev Cafe starts up every week. And remember to keep your curiosity open, your skills sharp, and we'll catch you in the next one. Take it easy.